Okay, so, um, it's really good to be back. I'd rather be here, than hashing out interviews. So, if I remember right, last time we ended with a problem like this, exactly like this. And I think we got through to, as far as I've written on the board, right there. Oh yeah, before we even started this problem, looking at this vector field, plotting this guy out, if you remember this vector field, what did it look like? Well, if you remember, the vectors were all kind of going in these, okay, I'm drawing it really badly, but it looked like things were moving along in a parabolic kind of way. So the vectors were indicating that if you threw a cork into the water here, that it looked like the cork would flow along in some kind of a parabolic curve, right? So in order to find the parameterization for this, well, the first thing was we took the vector field I plus xj, and what we're saying is that x prime of t, the x velocity of the particle, is always 1. There was not a function at all, so it's just constant. This guy over here, where we said the y component, the j component of the velocity is x. So here, when we put that down into our differential equation, we didn't just put an x. That had to become an x of t, right? This is a function of the x value at a given time. And so to me, that's one of the things that's just notationally that you need to get used to. And of course, it makes sense with complications, different ways you can look at it. But for me, learning this, this was always kind of a step that I had to make sure that I did correctly. Because if you don't do that right, then nothing really makes sense afterwards. So any x's or y's become x of t's or y of t's in the next line. So now we were able to go ahead and solve this system of differential equations, and we came up with the flow of f. Now, the flow of f, so this has a couple of empty parameters in here that we can plug in different numbers for. And so that says that this represents a whole family of curves. The flow is kind of every possible flow line that you could have for a given field. So in other words, depending on what you plug in here for x naught and y naught, that somehow relates to the position that the torque is at time 0. And then it flows along, depending on where it is at time 0, now it's going to flow along whatever curve it's on, right? So different starting points, generally different gravel. So that was the overall flow. Now, since we had an initial condition, we were able to go further and say, let's find the particular flow line that goes with this. And so we can find the parameterization for if the cork is floating along and it's at the point -2, 2 at time 0, then this is exactly the parameterization for that curve. It goes along the right path, and it's at the right point at the right time. Okay? So it's kind of filling in missing parameters from the flow in order to come up with the specific flow line. So in order to do that, we had to just kind of plug in our parameters, that the x at time 0 is -2, the y at time 0 is 2. And doing some work that led us to figure out what x naught and y naught were, -2 and +2. And so filling those things into our parameterization that we came up with, and filling that in, we were able to come up with our overall solution. And I'm just realizing back here, I left off the x of t part, and that's what's bothering me back here. So back here, this should have said x of t was equal to t plus x naught, and y of t was 1/2 t squared plus x naught t plus y naught. So, sorry about that. So in other words, Plugging in t is 0 for both of these, we know that this value has to be -2, that value has to be 2. And so we were able to find out what x naught, y naught were and fill them in here for our parameters. So now we've got the correct parameterization. So I believe, am I correct that we got that far last time?
That's
I've had a test in between, I rest my brain, I don't remember anything anymore. So the other thing is, so here, this is the parameterized version of the path, which has advantages and disadvantages. The parameterized version of the path is great because it tells us exactly where the particle is at any given time. The only disadvantage of the parameterized version of the curve is, I look at this and it's a little bit unclear to me, like, what does that look like as a graph? What does that curve look like, right? So I believe what we didn't get a chance to do a couple days ago was to now find the explicit path that this goes along. So in order to do that, all we're doing is we're saying we've got x is equal to t minus 2, and we've got y is equal to 1/2 t squared minus 2t plus 2. But what we want to do is we want to wind up with a function that's like y of x is equal to, well, y is equal to some function of x, so to speak, right? And so in order to do that, all we're going to do is solve this line for t, and then we're going to substitute that into our other line, and then we'll have y as a function of x, and hopefully that'll tell us more what the curve's like. So here we've got, t is equal to x plus 2. Now we substitute in x plus 2 in for these guys, and we get y is equal to 1/2 x plus 2 squared minus 2 times x plus 2 plus 2. And if we keep simplifying this thing down, actually what we wind up with is that. So in other words, these are two different ways of expressing the answer. And both of them have pros and cons. The pro of this explicit path is, I look at this and I go, oh, I know exactly what that looks like. I know exactly the shape that this particle's going to move along, right? 1/2 x squared, yeah, I got that in my brain. I know what it looks like. This guy here, I don't look at it and see it as easily. The problem is, what don't I have on this guy? I don't know where the particle is at any given time. Right? When I combine these guys, I actually lost information. So now I've lost the information of where the particle is at any given time, but at least now it's pretty clear to me that, oh, well, I don't know where it is at any given time, but I understand that it's going to go along this path. Y is equal to 1/2 x squared. So both forms are useful in different ways. Okay, so I just want to wrap that example up. Now, like I said, most differential equations, let alone systems of differential equations, aren't so easy to solve. Most of them require special methods, and that's why you have differential equations classes. Right? Because differential equations are nasty to solve. So put it this way, there's no kind of like one technique that works for all differential equations. With differential equations, it's a lot of recognizing kind of what the setup is, what type of setup is this, and then do I know some kind of a technique that somebody clever figured out for this setup. So it's a whole grab bag of different techniques. So you certainly can't be asked to solve like all kinds of random differential equations in this class. One of the things that I wanted to point out though here, and you know what, maybe this is a good exercise if we do this this way. So our next example. F of x comma y is equal to negative y I plus xj. So, you know, I can kind of get the idea that r prime of t, the path of the particle, the location of the particle at any given time t, or I'm sorry, I should say the velocity of the particle at any given time, that's going to be equal to whatever the velocity of the field is at the particle's location at that time, right? So this equation here that we're solving, written in vector form, that's really this differential equation, right? Because each one of those guys has an I component, and those guys need to be equal, and each one has a K component, and those guys need to be equal as well. And so what we get here is that, well, that says that x prime of t is equal to something and y prime of t is equal to something. What's this got to be equal to? What should go on this side? Negative y of t, right? These guys become functions of t when we drop them into the differential equation, otherwise things go all wrong. Similarly, this guy here isn't just equal to x, should be equal to x of t. So the idea here is that the I components are the same, the j components are the same, and these are all functions of t. So the problem is, if we jumped in here and we started just trying to solve this system of differential equations, it's not so easy. We would wind up kind of stuck without some special techniques of differential equations. But one of the things that sometimes comes in handy is if you look at what the field looks like, how all the arrows are pointing to the field, sometimes those guys will suggest a solution. Now, for example, the first one that we looked at, if you remember, all of the vectors were arrows, and we could see that they were all kind of, seemed to be pointing in these parabolic paths. So that kind of suggested that, you know, we should wind up with probably something parabolic looking, but this one was easy to do algebraically. We didn't need that intuition to get it done. For this one, the algebra is not so easy, but if we look at the field, that might suggest an answer. So here's what I'd like you to do real quick, is to make a quick plot of this field. And do that for the points 1, 0, 1, 1, 0, 1, and kind of all the way around like that. If you figure out what the vectors are for each one of those points and you plot those, it'll suggest a certain kind of a field. And then if we were to do this for more and more and more points, we would get a better view of the field. But these guys right here that I picked, they're enough to give us a pretty decent idea of what this thing looks like. So how do you make this plot? Well, for example, here if you start at the point 1, 0, then what you're doing is you're plugging in x is 1 and y is 0, right? So this guy here, f of, what was it, 1 comma 0, that should be negative 0I plus j. So in other words, it's just plus j. So that looks like a vector that is 1 unit long pointing along in that direction. Okay. So now, what does it look like if we do this at the point 1 comma 1? Well, plugging those guys in, we're going to get what? Negative I plus j. X is 1, y is 1. Okay, so what does that look like? Well, it looks like a vector pointing off kind of that way. Right? So if you keep going around the clock and doing these points, what's the vector for this guy look like? We have f of 0 comma 1. Let's see, so x is 0, y is 1, so that becomes negative I, right? So we get something like this. So if you keep going around the clock, well, take a minute to fill in a few more of these. So again, all we're doing is plugging in the coordinates of the tail of the vector. And then this will tell us what that vector looks like, what the I and j components are. So as you go around here and you plug in more and more of these guys, what you should see is a pattern like this. Well, if you were to drop a particle into the stream, say it was here at time 0, can you kind of see, yeah, it looks like it's going to flow around maybe in a circle, right? Looks like maybe it's going to get pushed around, something like that. That seems like a reasonable kind of idea. If we filled in more and more and more vectors, this idea would become more and more and more clear. And filling in more and more vectors, we would see that, oh yeah, this, we're going to have circular flow lines. Now, what I'm putting up here on the board, on the screen rather, is this is what our vector field would look like if we were to do more and more and more and more and more of this. So we have kind of, you can imagine, no matter where you throw the cork in the water, this thing is going to go around in this kind of counterclockwise motion in some kind of a circle, right? So using this idea that, okay, well, solving this algebraically is really not very nice. But what I do see is my paths are all circles and they're moving counterclockwise. What does that suggest maybe for a possible type of solution? How would you parameterize something moving around in this kind of counterclockwise circle? Sine and cosine, right? So x would be cosine and y is sine. Should be something like that, right? Now, there's different radii of circles, right? So what does that say about our sine and cosine? If it was just straight up y is equal to cosine t, x is equal to cosine t and y is equal to sine of t, that would only be this one circle of radius 1. So how could we maybe adjust that parameterization as a possible idea? Add a constant. So if we had, so we have the idea something like this, and y is, something like this might be a possible solution. But this is just radius 1. Now, if we add the constant over here, that's not really going to do what we want it to do. Right. How would we incorporate a constant in here?
Inside it.
So it makes sense that if this was like a 10, we would now, the x value would go from -10 to 10, the y value would go from -10 to 10, and we'd get a circle of radius 10. If it's 1, okay, circle of radius 1. So now we haven't tested this out, but this is kind of our idea of, based on looking at the vector field, I'm expecting to get circles, and so I'm expecting that maybe this is a possible solution. And this is we still haven't tested it, right? But this is just kind of our opening idea. How can we test that and see if it really works? See if it satisfies this guy here. By seeing if it is a solution to our system. Okay. So if it's a solution to this. So in other words, x prime of t, so that would say what? X prime of t would be equal to what? Negative k sine t. So x prime of t, so we've got negative k sine of t. Is that equal to the negative of y of t? Yeah, y of t is k sine t. So, oh yeah, this really is negative k sine t. Okay, so it satisfies the first part of this guy, it doesn't satisfy the second. Well, what would y prime of t be? So here we have y prime is equal to k cosine t. So there's our y prime. Is that equal to x of t? Oh hey, what do you know? So, as frustrating as this kind of is, because it's nice when we can just algebraically work things out, but using the techniques that we know so far, not having had differential equations class, if we try to do this algebraically with antiderivatives and that kind of thing, we find ourselves kind of getting stuck and not coming up with an answer. We don't know the techniques. But the idea is, and you'll learn this in differential equations class, probably this very example, is that sometimes by looking at the plot of the vector fields, sometimes that suggests an idea of, oh, I think my answer is going to be a parabola, or I think my answer is going to be a circle. And based on that, sometimes that gives you something like, well, maybe it's something like this. I don't know, but I can test and see if it really satisfies the differential equations. So, in your homework or on a test, there are kind of two main types of problems. One is, here's a simple system of different, here's a simple field like we did in the last one with the parabolas. We're able to just derive it all algebraically and come up with it, right? So there's that one where it's a system of differential equations, but it's one that we know how to do. The other type that you'll see is, well, here is a possible solution. Can you plug that in and show that it really is a solution or is not a solution? Okay.
So those are the kinds of problems that you're expected to do since it's not a differential equations class. Okay. Show you another one here that we can find a solution to if we think about it. And the setup looks almost the same. F is equal to xi plus yj. So using our basic idea of r prime of t is equal to f of r of t, that says x prime of t and y prime of t are equal to what? I component of this guy is x, so that becomes an x of t down here. And the j component is y, and so that becomes a y of t. Now this guy here, solving the field wouldn't necessarily give us super intuition into this. But if we think about it algebraically, we know a function that behaves something like this. This says what? This is a function whose derivative is itself. Do you know a function like that?
E to x.
E, yeah, so if you have something like e to the t, something like that. Oh yeah, the derivative of e to the t is e to the t. Oh, same thing down here, right? Oh, so it makes sense that this should, the derivative is itself, so maybe something like e to the t. But if it was just, so we're thinking like, you know, x of t is equal to e to the t, well, that works. That works as far as satisfying this, but could we make it more general? Yeah, we could add in a coefficient here. So if I said like a times e to the t, if I took the derivative of this, would I still have the same thing? Sure. How about this guy? I could add in a constant here. Does it need to be the same thing as that? No. Could be a different constant here, because here, all I'm trying to do is the derivative of this guy is itself. Okay, so fair enough. We have something that looks like this. So here, it wasn't easy to do algebraically in terms of like find an antiderivative and step by step and get this as your answer. But at least if you look at this and you see what it's saying, oh, I'm looking for a function whose derivative is itself, then that will trigger, oh, right, e to the t. That's that. So here's the parameterized version. See if you can find the explicit form of this kind of flow. So we're looking for something where y is some kind of a function of x. See if you can figure that out. So to find the explicit path, all we're doing is we're saying, take this equation for x of t and let's solve it for t. So first step here, solve this guy for t. So what have we got? We've got x is equal to a times e to the t. So I want to solve this guy for t, so what's that say? So x over a is equal to e to the t. So t is equal to natural log of x over a. All right. Now we could take that apart, we could wrestle some more with that, but let's just leave it as is. And now let's substitute this in for this guy here. So what we now have is y is equal to b times e to the natural log of x over a. What's e to the natural log of x over a? It's x over a, right? This is the power you raise e to if you want to get x over a. If I raise e to that power, I get x over a. Surprise, surprise. So y is equal to b over a times x. You sound like you want your minute. Too late, we're past that point in the semester. So we now have y is equal to b over a times x. So in other words, we should have straight lines, right? Well, if you were to plot the vector field for this guy, this is exactly what it would look like. So you can see that you drop the cork in the water and it goes flowing radially out along one of these lines. So this explicit form, it loses some information on where the particle is, or like, is it going this way or is it going that way? It loses a lot of information, but it tells us, oh, these things are moving along in lines. So we get this kind of radial field and radial type of flow lines. So this is just another example where this guy, looking at that field in advance probably wouldn't have given us that much useful intuition. I wouldn't look at that and go, oh, a times e to the t and b times e to the t, right? Nor if we tried to just do this, straight up, dive in, start taking antiderivatives, we're not going to get to this answer. But if we look at this and we realize this is saying, oh, we're looking for a function whose derivative is itself, that should trigger something. So I should probably move along because we missed a day the other day, and I sometimes like to do too many examples on these because I think that they're kind of good. And if that's wrong, I'll let you right. But we should probably move along and get started on chapter 18. So chapter 17 is a fairly short chapter, but we kind of learned two different skills. And in chapter 18, we bring them together to solve one of the real fundamental problems of vector calculus. So the things that we have are vector fields. Again, we can think of this conveniently as velocity vectors of water in a pond or whatever, right? And then the other thing that we have are parameterizations that can show the way a particle's moving. Now, the way we've combined these two things in 17.4 was to say, well, the particle has no propulsion of its own. It's like a cork that's thrown into the water, and it just floats along and it follows the arrows, right? Whatever the velocity of the water is, so is the velocity of the cork at that point, right? But now we can start looking at a new question. Put this away for the time being. And I already kind of gave you an introduction to this question. So this question has to do with that physics idea of work.
So again, the physics idea of work that we've gotten to so far when we studied vectors was the idea that, well, if we have vectors and we say we're applying some kind of a force vector to this wagon, but the wagon is going to not move off the ground, right? It's just going to move parallel to the ground. So we have some kind of a displacement vector here. Well, what we saw is, how could we calculate the work? Yeah, so what we saw is, and when we initially saw this, we did this with trigonometry, talked about the angle, blah, blah, blah. We could use a cosine, we could do all this junk, but that was exactly this, right? Because this just gave us the same thing. It said the magnitude of the force times the magnitude of the displacement times the cosine of the angle. Because mag f cos theta, that really gave us the horizontal component of this f, and so there you go. So this got, so in other words, that's useful to know sometimes, is useful to derive, but the main thing that we're keeping our eye on right now is that if the force is in a different direction than the displacement, then the work done by the force on the object is the dot product of F and D, right? So, now, this was better than our original definition of work that said, well, the force has to be in the direction of the displacement. Now we can, do problems like this, but it's still kind of limited that, A, what if the displacement isn't in a straight line? B, what if the force is changing? So what we've got here is, you can imagine, and again, I like to put this in the context of, here's a river, and you've got all of these velocity vectors. And so these velocity vectors that I'm drawing, this is the field F. So this is, F is what all these arrows are. And now, instead of just having a particle that has no propulsion and it just goes with the flow, now you can think of this as you are swimming in the water here. And so you don't have to necessarily just go with these flow lines. You could do all kinds of interesting paths to get from point A to point B, right? So here, call this, well, maybe I don't want a vector on it, but this path, we could parameterize our path where we are at each time, and we could come up with a parameterization for the path that we take that would be our R of t. So here's the thing. What we want to calculate is how much work does the river do on us as we swim along the path from point A to point B. That's what we want to know. Now you can imagine if, well, before considering this complicated path, imagine that we did the simplest thing possible and we just kind of went with the flow like in our previous problem, and we're just going exactly in the direction that the river's going, right? It's kind of following the arrows. Well, if we had that, then wouldn't it make sense that we could kind of say, well, I could approximate the work by saying My arrows go in the same direction as this arrow. So if I follow this little, if I imagine following this for a straight line for a short distance, how much work is going to be done? Well, the river is going to do F dot D amount. My angle is 0. So this guy here, which was mag F mag D cosine theta, is that going to be positive or negative? It's going to be positive, right? Oh, cosine of 0, that's 1. Okay. So, all right, so now I float along and now maybe I'm here. Now I imagine, well, what happens if I just went along this arrow, straight along in that direction for a while? How much work would be done? Well, on that amount, the river would do F dot D amount. Once again, the angle is 0, so it'd all be positive. Okay, so if I kept adding that up, adding up how much work, how much work, how much work, how much work, kind of breaking this up into pretending I was moving along straight little line segments, it would kind of make sense if I added up all of those guys, I should get an approximation of how much work the river does on us as we go along. And here you said that if I was going exactly along with the arrows, then all of those guys would be positive amounts, right? So it makes sense that the total work that the river does on me as I swim along following the arrows would be some positive amount. Now, what would happen if somebody else was coming the other way? And here, they're always following the arrows, but they're following them in the opposite direction. They're following them head on, right? So they're going against the current. What's going to happen if we break up their path into a bunch of little line segments and we add up the work that the river does on them as they go along? F dot D, what's that going to be? Because the angle is going to be what? Yeah, the field's going that way, but the person swimming's going that way. So you got 180 degrees. What's cosine of 180 degrees? Negative 1. Oh, so all of these guys are going to be negative quantities, right? So what's going to happen? A negative plus a negative plus negative plus negative plus negative plus a negative. So here, if they were going directly against the flow, so to speak, then we'd say the river is doing a negative amount of work on them. So what does that mean? If I'm going with the flow, more or less, I'm winding up with a positive amount of work that the river does on me says, is the river kind of making things easier or harder for me if it does a positive amount of work? Makes it easier for me, right? I'm going with the flow. The river's doing work for me, positive. On the other hand, if I'm going exactly opposite, I'm fighting the current every inch of the way, then that's going to come out to be a negative amount, and that says that the river was kind of making my job harder as I swam along. So the question then is, so the sign of this, positive or negative, that tells you overall, was the river helping you or making your life more difficult? So this guy here, though, it's a little bit harder to tell. Is the river helping or is the river going against this guy? Well, the answer is, I don't know. Because as I go along here, sometimes I'm more or less, the river is more or less helping me, even if it's not totally helping me. With this dot product, again, this is really mag F mag D cosine theta. What kind of angles make this positive? Yeah, if I'm kind of less than 90 degrees, then this is positive, right? Which means that the river is kind of doing some of the work for me. So, if the angle between my path, where I'm at, and the field, the river's velocity, is less than 90 degrees, then overall, that's kind of helpful to me. This comes out to be positive. On the other hand, what happens right here? Well, at this point, I'm trying to make it so it's like a 90-degree angle there. Don't think intuitively, it was made up by physicists, there's nothing intuitive about it.
Zero.
But yeah, 90 degrees, right? So here, technically, the river is doing zero amount of work on it. And then, when you turn the corner and you start doing this, and the river's, moving in this direction, you got an angle greater than 90, now you're fighting the current, now 90, you're greater than 90, and so this becomes a negative amount of work, right? So does it kind of make sense that on some parts of this path, the dot product is positive, and so the river's helping us? Right here, we're at a balancing point where it's not, supposedly helping us or hurting us. The analogy breaks down if you think about it too hard, so don't think about it too hard. And then when we turn the corner and we're more or less fighting the current, oh, well, now we're racking up some negative work. We've got a bonus, but now we're having to pay some of it back. Now we turn around again, and maybe we get a little bit more of a bonus. So the idea here is we're adding up dot products for a bunch of little segments, and in simple situations at least, we should be able to predict if the amount of work that's done is going to be positive, so the river was helping us, or if it's going to be negative and going against us. So, for example, if you were to swim from here to here along that path, well, we're not going exactly with the current, but overall, what do you think?
Positive.
Yeah, overall, it should be positive, right? If I break this down into a bunch of little line segments and dot products with the field vectors, the angles are less than 90, I'm just adding up a bunch of positive things. And it makes sense, the river's doing a lot of the work for me as I swim along the way. On the other hand, if we were to reverse the path and come back this way, now it's the other story, right? If I was going the other direction, I'm fighting the current, I've got an angle more than 90, I'm getting negative dot products, negative plus negative plus negative plus negative plus a negative. I'm paying a penalty for going against the river, right? So we'll pick up on this a little bit more tomorrow, I'll make it a little bit clearer. But this is the big idea, and the overall problem that we're doing is something called a line integral. Line integrals are a really key thing of electricity and magnetism, very, very useful